going deeper because there's another super tech coming along, and this one, you've probably all heard it, it's going to completely transform the computing landscape. It's going to make all of the computers we're using more or less obsolete. To tell us about that, please welcome to the stage Professor David J. Reilly. Professor Reilly is the principal researcher and director of the Microsoft Station Q project at the University of Sydney. I'll be sitting down in conversation with Dr. Reilly after he finishes his presentation, so hit the Slido and ask some good questions. Welcome.
Thanks very much. So you may have heard in that introduction there, and if you're looking carefully at the logos that are on this slide, you'll notice there's a University of Sydney logo and also a Microsoft logo. And it represents a partnership that has just started only a few kilometers from where we are at the moment on the campus of the University of Sydney to start to advance the engineering frontier in order to develop a prototype quantum machine of a kind. What I want to tell you about today is some of that work, but give a context for the discussion as well of what quantum computing really is and what are some of the challenges that we face to see this technology become a reality. Quantum computing is a subset of quantum technologies, and we're still in the business of learning what the fundamental reality, our most successful theory of nature, may enable in the technology space. We do know that physics of quantum mechanics is distinct. It's different from the classical physics that we've built all of our other manufacturing, all of our other technology around. The physics of Newton, physics of bowling balls and inclined planes and all of that great stuff that you might have learned in physics in school, that's the classical physics that really enables our world today. And yet there is different rules of nature. There is an entirely different logic in which we can construct devices, machines that process information. 3 examples, it's not an exhaustive list, but 3 examples of where quantum mechanics is vastly different from classical physics. These areas of superposition, that is the wave-like behavior of nature. Down there at the nanoscale, if you were to zoom up on this table and look at what it's built from atoms and electrons, nanoscopic objects, 1/1000th of a meter. Those things actually behave in many ways like waves. They have a wave-like character. We don't today harness that in many of our technologies. It underpins our understanding, for instance, of materials and the like, but we're not really exploiting the wave-like nature of materials, the wave-like nature of the way in which our reality, the way in which our world is actually built. Quantum measurement is even more philosophical. It's a cartoon there that tries to poke fun at the idea that measurement, observation of a system in some way disturbs or interacts with that system. Is that a resource for technology? Can we use, for instance, the act of measuring something as a means of determining whether an eavesdropper has intercepted a conversation? You may have heard of quantum communication, secure communication. It's based on that unique piece of physics that the act of observing, of measuring, of reading, of detecting even a single photon disturbs it in a way that we can realize. Up the other end, I have no analog of the totally mind-blowing physics that is quantum entanglement. Any attempt to try and explain that, I think, falls short. The closest I can really come is to say that nature permits correlations and connections between objects at the quantum mechanical level, even if those objects, for instance, are separated by vast distances. Those connections, those correlations, allow us to transfer potentially aspects of a computation, distribute that computation across a chip in a way that's impossible with classical technology. I'll say a little bit more about that maybe in the conversation at the end. Taking those 3 unique pieces of physics that today we don't tap for technology, you can play out what the future may look like. It spans supercomputing. And I think when people say quantum computing, traditionally what we've meant is supercomputing. Probably the low-lying fruit to pick is in the sensing and imaging area. In the next few years, we're going to see quantum mechanics show up in our ability to detect diseases in an MRI, for instance. harnessing aspects of those pieces of physics that I showed in order to increase the sensitivity of all of our instruments. It could be in the mining sector, it could be in medicine, it could be in aviation, and so on. As machines are constructed, somewhere between the supercomputer and the basic physics devices that we have today lives a killer application. The area of quantum simulation or quantum emulation, which dates back to Richard Feynman, the idea that if I could build a system out of some quantum mechanical elements and I had control of that system, I could use it to emulate another quantum system. I'll give you an example in just a moment of where we think that will be incredibly powerful in the area of pharmaceutical development, in the area of catalyst development and new materials. The other areas are kind of a little bit disconnected. Precision measurement, metrology science, I've mentioned already security and communication, and of course, the thing that really drives us scientists, new physics that we may uncover, totally new understanding about how our universe works, if we could construct a machine that actually exploits quantum physics. Around the world today, you'll see a race. It's a race that spans universities and now major industrial partners, government laboratories, to realize devices that can, because of their design, exploit some of that physics that I showed you. Quantum superposition, quantum measurement, quantum entanglement. How do I reach down and grab quantum entanglement and put it on a chip? We don't know the answer to that. It could be that you want to embed it in the state of a photon of light, a photonic system. We know already that light has a wave-like character, and it seems an obvious choice to manipulate that wave-like character in order to be able to entangle photons and distribute them on a chip. We don't really know how to scale that technology, though, into a complexity class that makes it useful. So the jury's out as to which is the most scalable technology. It could be superconducting qubits, IBM and Google are currently pursuing. It could be ion traps, which have been around for a long time. Very impressive technology, but again, it's not clear how they scale up into very large, complex systems. Or some of the more newer approaches, for instance, what I've called here Majorana qubits or topological qubits, that's the approach that Microsoft, for instance, is pursuing at the moment, that we believe is going to be the most robust means of realizing quantum mechanical devices, or qubits. How does it all work? I'm sure you've heard of qubits, I'm sure you've heard of quantum computing, and if you read the newspaper or so, you'll see either Malcolm Turnbull or Justin Trudeau trying to explain quantum computing as, well, classical computing is a 1 and a 0, and quantum is both at the same time, and at that point I'm lost. I don't know what both at the same time really means. It sounds good. I don't come away with a deeper real understanding of what's going on. So let me try my luck at getting across at least some of the essence of how this technology actually works. Looking to VLSI, traditional classical information processing, logic is encoded in the state of a switch, of a transistor that's obviously open or closed. And a key aspect of our modern life and our economy today is built around not just the encoding of information in the state of that transistor, but the realization that the transistor itself can switch other transistors. The state of that transistor, whether it's open or closed, whether it's representing a 1 or a 0, can go on then to affect the state of another transistor and fan out into very complex logic trees. That fan out is possible, is essential to the technology we carry around with us in our pocket and drive our economies. It's not clear how quantum devices work in the same way. How do quantum devices fan out? So what do we mean by a quantum device? I've kind of given you a sense that there's various physical platforms in which you can encode quantum information. That's maybe a complex way of saying that I need some energy states. I need a splitting between the ground and excited state of some system. That system could be an atom. It could be the inner and outer shell of electrons inside an atom. And I could encode those energy states, the excited and ground states, as a 1 and a 0. But it could equally be the charge, the spin, the vibrational mode, and so on, of many different systems. So long as I have an energy level splitting of a kind, then I can encode information in the ground and excited state, and in fact manipulate that information into states that physicists would call as superposition. That is, that rather than just be in the ground or the excited state, those two different energy levels, in fact, I can encode information and manipulate it such that I'm in both of those states with some weighting. Okay, so it could be, again, an electron in an atom. Rather than it be in the ground state or in the excited state, when we say both at the same time, what we really mean is that the state of the electron is living in both a little bit of the ground and the excited state with some weighting, with some coefficients, until a measurement of the system is made. When I make a measurement, I will always find the system in the ground or the excited state. So they're the two ingredients that I actually need in order to be able to process and manipulate quantum information. I need some energy splitting. I need two levels to manipulate. Obviously, if I had more than two levels, one could also encode in some kind of higher states. But for a binary kind of representation, that is a qubit, two levels are sufficient. And I need to be able to control which state I'm in with some coefficient of whether I'm a mixture of either one. Read them out. For a moment, I want you to just imagine that you have the challenge now of encoding information in these energy states of a system. I'll stick with the idea of it being atoms. I need some device, a classical, could be laser or electronics, that allows me then to manipulate those states, to write and read from them. It's a little bit like, now I can say, an old-fashioned hard drive that reads and writes magnetic domains into a magnetic material. And so putting a qubit in a one state is really about aligning, in this case, it's a magnetic domain in the up direction as opposed to the down direction. Each one of those magnetic domains has some kind of analogy with the state of a qubit, if you can then imagine that those domains can point not just up and down, but they can obviously point in any arbitrary direction in a superposition of states. So it's a little bit like DRAM. It's a little bit like how you can imagine writing the state into memory and it's staying there for some finite lifetime before you have to come along again and either read it or refresh it. And the game at the moment in quantum computing is how to take these physical systems that I've shown, embed them in some kind of classical controller hardware, often operating at extremely low temperatures, just a fraction above absolute zero, and control them on timescales such that, like again DRAM being refreshed, that information is not lost. We can't store it arbitrarily long. One has to manipulate the information, carry out the computation within some kind of lifetime before that charge state or qubit state relaxes. Okay, so I mentioned before that our classical devices fan out. Transistors switch other transistors. Logic gates can drive other logic gates. That's how we're able to build circuits that, for instance, add or multiply and carry out all mathematical operations. How about for quantum computing? Is it possible to have quantum gates, these superposition states, these energy states? Do they fan out? Or how am I going to build actually an algorithm and a quantum computation around it? Well, it turns out that, in fact, there is a theorem of universality around quantum computation. One doesn't need to be able to perform any arbitrary logic operation. In fact, you can choose just a subset. I think two or three of these operations are sufficient to build a universal quantum computer, just like if you can realize a NOT gate or a NAND gate in conventional logic, you can use that to build all the other logic families. The same is true in quantum computing. If I can realize a gate that just flips the state of the qubit from 1 to 0, and if I combine that with a gate that allows for two qubits to interact, that is fan out, one affect the other in some way, then those two ingredients taken together, played out many, many times and scaled up, allow for universal processing of quantum information. So that's good news. One can imagine then a quantum algorithm proceeding a little bit like the music in a score. Instead of playing the notes on the piano in time, I'm playing the various logic gates. These H's and S's and U's represent manipulations on single qubits, that is, manipulations on energy states. one at a time or in parallel, as well as interactions between the two of them. So I've kind of taken a bit of a deep dive there into the details of how quantum computing works, but I hope it gives you a bit more of a sense, particularly if you're familiar with our classical means of processing information with electronic computers, how this world might actually work. The challenge is to build qubits, that is energy level systems in some physical platform, and be able to manipulate them, encode and read out that information in order to carry out some kind of quantum algorithm. So why do it? Sounds cool. It's fun to kind of, build a calculator into atoms or something. But what's the real game here, and why are companies, for instance, like Microsoft, so interested in this field all of a sudden? What's the killer app? The truth is we don't really know. We have some glimpses, but we're still in the business of trying to work out what this technology is good for. And that's by no means an excuse. I personally draw, for instance, a lot of inspiration from the history of classical devices. I think you can go back and read about what people thought transistors were good for when they were first invented. Does anyone know? The first killer app? I mean, vacuum tubes were around, ENIAC was around, very large computers were around.
Doing the census for the United States because of the census?
I think that was one of them. I think that came a little bit later. Did you have one?
No, that was from the IBM, the census in the US.
Exactly. Prior to that, when at Bell Labs they were building these devices, they had in mind repeaters and reliability issues. But the first application that they realized when it was shown to work was hearing aids. Well, it's small. I can't put a vacuum tube in your ear. But I could put this tiny transistor in your ear. It went away pretty quick. They realized maybe that's not such a great application. But I think it's super interesting to look back and think what powers our economies today. Only 50, 60 years ago, we couldn't see past a hearing aid as the killer application for that technology. Quantum computing, we do know of applications where it's going to be powerful. We do know that there are areas that if we had a quantum computer today, we would apply that power and do something useful. But I really want to kind of underscore this idea that it's evolving. It's an exciting field that's still developing. We're still trying to understand what it's good for. Richard Feynman, a famous Nobel Prize-winning physicist in the 80s, realized that simulating quantum devices, simulating quantum systems, they could be molecules, they could be drugs, they could be atoms, for instance. That's a really hard computational problem for our supercomputers today, let alone back in the 80s. A lot of the time spent on supercomputers today is in drug design, is in understanding aspects of material science. Very hard problems to simulate large numbers of particles interacting electron systems with classical machines. An approach to that is to build a quantum computer, not because they're just powerful somehow, but a quantum computer is a quantum system that can emulate another quantum system. So the idea of quantum simulation, I think we're going to be seeing this idea play out over the next 10 years in a very serious way. Quantum simulation using one controllable quantum system, a small-scale quantum computer, in order to be able to study a less accessible quantum system, perhaps a drug or a material. What questions could we answer if we were able to simulate the quantum world? Teaching a subject called condensed matter physics at the University of Sydney, I often make the point that you can go out to the road and scrape up, whatever you find. Often you might look out the window of your car at the traffic light and there's random stuff there. Usually there's glass because there's been accidents, and there's a bit of other stuff, there's some grass and some rocks. And if you keep looking, you see really weird things in there. There's a little bit of a toy, and then there's someone's skateboard that's whatever, and a whole random collection of just stuff. Go and scrape that up. And now I give you the challenge. Tell me what it is. This is a question I ask the students. Tell me what that is. How would you find out? Oh, that's easy. I can do that. What would you do? Well, I might put it in an X-ray machine. I might do gas chromatography on it. I might do all of this analysis that we can do today. And you will find out not just what it is. I'll tell you exactly what it is. I'll tell you exactly what atoms are in it. I'll tell you what its thermal properties are, what its mechanical properties, what its optical properties are. I'll tell you what manufacturing plant built it. I'll tell you, the concentration of radioisotopes in the particular carbon, and on and on and on. I want to invert that problem. Rather than let me give you some random stuff, tell me what it is. I give you the periodic table. Pick whatever elements you like out of the periodic table in whatever combination you like. I would like a superconductor. I would like a material that is harder than diamond. I would like a material, in fact, that has amazing thermal properties, optical properties, mechanical properties, and so on. Combine the elements in the periodic table and give me the desired property. We have no idea how to address that problem. We can analyze things and figure out the constituents. I can't give you the constituents to construct a designer material. Why can't we do that? We have supercomputers. Why can't we do that? It's computationally impossible. If we had a quantum computer, we're in a different regime of being able to assemble elements and understand those properties in a way that we just don't have access to today. Let me give you just one example, because I do want to impart that this is real, and it's more than just super powerful computers, but rather computational paradigms that will be very useful, very powerful in certain areas, but in fact they won't replace all of the classical computers that we carry around with us today. One example is in the area of finding an efficient catalyst for the Haber process. The Haber process is a way of making ammonia. You take nitrogen and you take hydrogen and you push the two together. They don't like to go together, and if you want to make ammonia, you have to use an enormous amount of energy, generate an enormous amount of heat, generate an enormous amount of greenhouse gases in order to make fertilizer to feed the world. Take fertilizer away from the world, and it's pretty hard to grow crops in most of the regions of the planet. Very important that we have fertilizer, but boy, it's pretty inefficient to make ammonia that we need for fertilizer. Why is it so inefficient? We don't know. But we do know that nature, that evolution in plants, they can do nitrogen fixation out of the soil at low temperature without enormous pressures and energies and heats. Nature has figured out a way of doing it. Recent paper, again, this is work from Microsoft Quantum, has shown that if you had a very small scale quantum computer, you would be able to shed light on the question of how you realize an efficient catalyst for the Haber process. Being able to create catalysts that allow for this reaction to take place in a way that is much more energy efficient. And the reason I'm highlighting this, you can look that paper up, it's freely available. That's a long paper, and the details are spelled right out about exactly how you would go from qubit technology through to impact, not just being able to realize and solve this problem, but then what that problem would enable. What does that do to our economies? What does that do to our society when we can start to address questions like that? Hopefully, I've given you a bit of a glimpse of why the field is exciting in terms of its long-term impact. Many companies now, large companies, are getting in on this, all with their own approach. Microsoft, I would say, is unique in some ways in that it is attacking the problem it's attacking the full stack. I think it's an American expression to say from soup to nuts. I said I prefer the Australian one, which would be from soup to scotch. I don't think people finish meals with nuts anymore, but from soup to nuts, from hardware, from mathematics, from computer science, from the engineering, from the applications, from the business model, Microsoft has assembled a team to address that entire spectrum of challenges and to have those different slices interact with one another in order to be able to develop platforms that are going to answer the questions that we're interested in. So I'll wrap up. If you're interested in reading about that partnership that's happening here in the city of Sydney, on the campus of the University of Sydney, you can read about it in the New York Times. There's been a series of articles about Microsoft's investment and enthusiasm to do this and to use the solutions that may come from such a machine to the benefit of society. So I'll stop there. There's some obvious questions about how one might access such a machine. I'll leave that image up. I think that probably gives you the answer. Thank you.
Okay, folks, you are madly typing your questions into the Slido, right? Because you know exactly what you're going to ask. I'm going to start. How far away is, and we can do quantum computers that can handle about, what, 6 or 10 qubits simultaneously, so it's like basically like having a small computer. How many do we need before they start being useful for the kinds of problems they're talking about, and how far away do you reckon that is?
The field began with the realization that a quantum computer could be used to factor really large numbers into its primes, and therefore would attack RSA, public key cryptography. And it was the United States government that realized that might have some impacts for security, and one should, in fact, start a program to understand how easy or how hard a problem it is to build a quantum computer. That was in the late 90s, early 2000s. Right. And if you were to ask me the question at that time, the answer would be you need millions or even billions of qubits before you would be able to factor numbers that are sufficiently large that the machine would be useful.
Right.
Every year since that time, we see more and more examples of where very small-scale quantum machines, I don't want to even call them computers in the conventional sense, are becoming potentially useful. I've given you some examples of quantum simulation where we think if we had something like maybe 50 to 100 logical qubits, then we could start to attack these questions of for instance, efficient drug design or finding catalysts to accelerate reactions. There's an entire different paradigm of computing that's also emerging at the moment to use quantum mechanics not in that kind of conventional circuit, what's called the circuit model approach, that score of music with the notes and I play out the different logic gates, but rather other ways of embedding quantum mechanics. And I think not a month goes by before you see other examples of where that's taking off.
Is that because it's taking us some time to unlearn classical computing and start to think around what the capacity of a quantum computer is?
I think that's true. I would liken it a little bit to imagine I said, hey, can you write me some computer software, maybe an operating system or something pretty serious. Don't do it on a computer. I'll just write it out with a pen and paper. I'm not going to get very far if I don't have hardware in which to hack the thing. So I think it's slow progress trying to figure out what the right algorithms are and what this is going to be useful for. But as the technology emerges, the hardware emerges, and we release that hardware, unleash that hardware to the world, I think it's going to be a 16-year-old in their bedroom that figures out what to do with 47 qubits that we didn't think of.
And if that 16-year-old breaks RSA, there's going to be a very interesting problem. Do we have any hands with questions in the audience? We have a couple of really good questions on the slide. Does anyone have a question there? There are claims, this came from Bill, there are claims that either 51 or 49 qubits are currently working. Do you believe those claims? That's a lot of qubits, right? Do you believe the claims that are being made about?
So certainly Google has been very public in identifying the number of qubits of that order for which they could make a claim of what's now being called quantum supremacy. That is, they would be able to perform some kind of computation that is impossible with a classical computer of any kind.
Right.
Not just next year's classical computer, but of any kind.
Right.
When you drill into the detail, though, it's a kind of hand-picked, handcrafted problem that they're solving. It's an esoteric math problem for which nobody's really interested in. So it's a pretty artificial game to play. Having said that, I mean, I think it's an interesting goal. I'm not aware at this point in time that Google is anywhere near where they had hoped to be at this point of the year.
Okay, so let's say I had a magic wand and bammo, you have a quantum computer. What's the first thing you do with it? I
would definitely use it to design a better quantum computer.
You are a researcher. It's not a bad answer, and that's basically what Feynman said, right?
Yeah.
Yeah, and that you'd use this.
I would put it this way: the area of quantum computing is it's pushing the limits of all of our current technology. And if you're somebody that's interested in, how do I get in on this without being a Microsoft or a Google? I don't think you have to be building quantum computers. I think that the whole family of technologies that are needed to make this happen don't exist. And if it's a gold rush, maybe it's a good time to invest in shovels, and maybe you want to be a shovel manufacturer. We need tools, we need instrumentation, we need people who understand a little bit of this stuff enough to be able to provide a component or a piece of the puzzle. And there is, I think, a quantum economy that is going to spring up around these grand challenges. It doesn't exist today.
I like that. So one of the other ways you could characterize it is as a bit of a phase transition. To give you an example of what I'm talking about, quite good friends with Gavin Andresen. He's the chief scientist at the Bitcoin Foundation. And after he got the job, I was like, oh, so you're designing better Bitcoin? He's like, no. He says, I obsess about what happens when we have a quantum computer that can break the maths that all blockchain and pretty much all modern cryptography is based on. Do you see that as, as soon as there's sort of enough of a working quantum computer, does the entire world suddenly become insecure for a period of time because we can finally solve some of the math problems that are no longer soluble?
I think the answer is no, but you should worry.
He's not a stupid man, so I'm assuming he's worrying for a very good reason.
We have already realized classical encryption algorithms that are robust to quantum computers.
Right.
Okay,
Yeah,
so that's
cryptography.
exactly, and there's large areas of development underway to improve that.
Yeah.
So there are ways of protecting your money. I think what you would worry about is if you were a government perhaps that had used public key cryptography or related
say
algorithms,
Estonia.
exactly, or even the United States, to hide your government secrets over the last 20, 30, 40, 50 years. So.
Right.
Let's say we switch into robust algorithms that are robust against quantum computers today, which is more or less happening, but the secrets of 5 years ago will still be pretty saucy information in 5, 10, 20 years' time from now, and that's a big issue.
Do we have any questions from the audience? It's one in the back there, one in the front. How about down here? Okay.
Hi, my question is about quantum entanglement and the effects we see there. You can separate two photons and see the same effect on both. Are we likely to ever be able to use that as a communications mechanism? Can we affect one and see the effect on the other? Because I'm not clear whether that's possible or not.
Yeah, it's impossible, is the answer. It was the obvious application that people had in mind the moment they realized that this spooky stuff was in fact real. And it has a deep and rich history. It was an experiment, a thought experiment proposed by Einstein and co-workers, not because Einstein didn't understand quantum mechanics. People often say, this stuff broke Einstein's brain or something. I think he understood it so deeply that he realized that it was suggestive of incredible things like entanglement, that if quantum mechanics is true and complete, then it must permit quantum entanglement. And so he proposed a thought experiment to verify that. And it turned out that in fact is possible. And once people realized, people like the likes of John Bell, that in fact entanglement is real, immediately the next idea was let's use it for faster than the speed of light communication. It doesn't work. And the reason it doesn't work is because there's no way of knowing the state of the particle on the other side of the universe, even though it's correlated with your measurement outcome. So it's a little bit like this. I give you a pile of coins, and I have a pile of coins. Let's toss our coins separately. And I get a head, and then a tail, and then a head, and then a head, and then a tail, and you get some other distribution. It's not until I call you up or we get together and we say side by side, your head is my tail. Look at that. Without the comparison, all I've got is just a random 50-50 mixture of coins. So I can't communicate. I can see that they're connected and there's a correlation, but I have to call you up and use classical communication in order to be able to compare that. That doesn't mean it's not useful. I mean, it's a little bit like voodoo. Imagine voodoo turned out to be true and you said, as technologists, guess what? Voodoo's true. You can take a doll and stick a pin and someone on the other side of the city feels a pain. Who wouldn't be thinking, well, that's a product. That's an industry. It's true that we don't use that piece of physics in all of our technology. We're yet to exploit that amazing piece of physics. I think in our lifetime we're going to see that turn into a billion-dollar industry of entanglement.
Okay, so Project Q is actually a whole bunch of universities, right, that are all over the world. So what's Sydney's role in the whole picture, and what's the whole picture look like?
Yeah, great question. It's a consortium really of the University of Copenhagen, TU Delft in the Netherlands, and the University of Sydney. There's a theory effort in Santa Barbara. Something very strange has happened. Rather than the usual model of a large company funding university research, in fact, it's much bigger than that, and it's very different to that. I'm now a full-time Microsoft employee. I also hold a university position, and that's true of my colleagues in Copenhagen and Delft. So Microsoft is us, and there are engineers and the like that are part of our teams. And it's a partnership between university and industry that I don't think either one's seen. Certainly Microsoft has not done this before. Certainly the University of Sydney has not done this before. But we think it is the way to do it. It's a field that is still very much fundamental basic science. It's student PhDs, it's research papers in Nature, and so on. That's going to continue for decades. But it's time now to throw serious engineering power at it and to treat it like a product, and to switch into a mode where we can advance that frontier that's just not really possible in a university alone.
And are the various universities doing different parts of the problem, or are you all sort of?
Yeah, there's definitely a divide to some extent, although it's not very opaque. There's a lot of mixture between the nodes. Sydney's role is...
A lot of entanglement.
Exactly. Sydney's role is very much in the translation of the fundamental research into engineering and scale-up. And so the question of scaling, I think, is one that we're passionately pursuing. It's really hard to figure out whether things scale. The approach we're taking is to try and do it. So Sydney is one part engineering, one part physics, and I think it's going to be the place where it all kind of comes together and where we switch on these basic first prototype machines.
So it's a good question from the audience, which is, it's asking, given that this is sort of it is a new paradigm, do we need new maths to go along with the new hardware? Are we seeing the evolution of a new maths in the same way that classical computing is grounded in a sort of algebra, right? Yeah. Are we seeing a new maths emerging as part of this?
Yeah, I think we're seeing a new field that includes many aspects of mathematics and physics, the field of quantum information theory, and how to not only realize quantum algorithms, but how to encode information in a robust way, how to correct errors when, as I showed, one of the basic kind of foundations of quantum mechanics is that measurement affects the system itself that you're detecting. So how am I going to do error correction and error detection when if I measure the thing, I disturb it? So there are approaches to that. And it's a really rich area that definitely involves a lot of math and a lot of basic fundamental theoretical physics. The Microsoft effort started and continues to be led by Michael Friedman, who's a Fields medalist in topology. I was speaking to him literally.
Fields medalist, mathematical equivalent to the Nobel Prize.
Exactly. I was just speaking to him on my phone 5 minutes before stepping on this stage about some of those details. And I think it's an example of where the math that's in Mike Friedman's brain is shaping what we're doing in a lab in Australia with engineers.
He's at Microsoft now?
Yeah, absolutely. Yeah.
That's huge.
Yeah, definitely. Yeah.
All right. We talked about the importance of simulation. A lot of my own career has been about developing classical simulations. And of course, there's a point where they just become intractable. They become too big. But you can clearly see now how important that's going to be for science, but also for medicine, because we cannot simulate a cell now. Exactly. So is that part, is a sort of, I guess, a center point of 21st century medicine, the fact that we have quantum computing?
It's a really good question. It's again, an open area for people to advance the frontier between, I'll call it, biomedicine, both how does biology use quantum mechanics, and how can we further medicine if we have machines and technology? It could be in the area of imaging and sensing, as I showed. But what edge do we gain from using quantum logic or quantum physics as opposed to classical physics in developing the tools and instruments that we need? Certainly in my own group, in addition to computing, we also have an activity in developing new technology for MRI that borrows many of the discoveries from quantum computing and applies them to developing new ways of detecting disease.
People basically don't know that MRI is a quantum exam, right? You're spinning all of your protons. Oh, look! And
you bet.
Yeah,
absolutely.
Okay. Last question from the audience. Anyone? Come on. Is there where? Oh, yeah, there's one back there. Sorry. Thank you. Get that man a microphone. Quick. Yes, but we need you for the record, sir. There we are.
Are we at risk of ending a bit like fusion reactions, where that's really well understood, the physics of it, And yet, despite millions and millions of dollars, billions of dollars, and clear, massive beneficial outcomes, we still haven't got there. You're in a much more complex and, let's say, less well understood area. Could we end up with the same frustration for the same 50 plus years?
It's a great question, and it's one that keeps me up at night. It's definitely possible. I would say that maybe a little bit different from fusion is the impact that it would happen if it turned out not to be possible. So from where we stand today, the physics of quantum mechanics permits quantum computers. If it turned out that there was something that actually stopped that, that would suggest that we don't actually have a complete understanding of quantum physics. If there was a showstopper that appears, it could be that, yeah, you know, you can build out these qubits, but when you get to 147, new laws of physics switch on. There's an emergent complexity that we didn't see coming. If that turns out to be true, it's probably more exciting and more impactful than building a quantum computer. That could be good news. The bad news would be that it's totally possible. It's a really hard engineering challenge. And I think that's where fusion's at to an extent. I think it's important to realize that fusion didn't go away. We don't hear about it much. It moved out of very much university research, but there are large efforts to still realize fusion. They're extremely expensive. And it may well be that it happens. I don't think people have given up on that. The impact, obviously, of fusion would be comparable. Similarly, the world's thirst for computation is not going to go away anytime soon. And so I think it will just increase the resources that we put into this problem. And my view, seeing the progress in the field, seeing what lays before us, as hard as it is, I think it's possible. I think we're going to see it happening in the coming decades.
Ladies and gentlemen, let's all thank Dr. David J. Reilly.